show this up. It's called the fishing spider. You should show them how it uses its it basically uses its legs on the surface tension of the water to stay afloat to catch like fish and stuff and other bugs.
The fishing spider?
Yes, it's called the fishing spider. It's pretty cool. You should.
We can check that out.
I found this on like Animal Planet a long time ago when I watched like the different types of spiders. Yeah, it's pretty cool. The fishing spider. Yes. It's pretty cool. It floats. It uses its back feet to actually. I don't know where part of it shows you.
Phobia, so this is terrible for me.
Yeah.
I know it's bad.
The same force keeps the insects afloat as is keeping that coin afloat. The water binds to itself so tightly, the spider is not heavy enough to penetrate the surface tension of the water. So it looks like it's standing on the water because it's the surface tension holding it up.
Yeah, it's actually pretty interesting to like look at how it moves in the water. Yeah, isn't that crazy? It can swim and everything.
Yeah, that's the surface tension holding it up. We can't do it with American coins. American coins use copper and nickel, and it's a lot heavier, and they'll sink no matter what. But the Japanese coins are pure aluminum, and they're light enough for this to work. What's that?
It'll eat the fish. It's called the fishing spider because it eats minnows. It's cool. It goes underwater and it'll eat the minnows. It'll like catch them, and then it's kind of, I don't know. It's so strange. But it'll actually dive underwater to grab the yes, look at that. Strange creature.
Yeah, there's surface tension at play.
It's like hot now.
What?
I have a really bad fear of spiders, so like just seeing them makes me want to like cry, and I just get really warm and like I just start sweating.
Have you ever seen those pranks where like someone closes their curtain and like a fake like camel spider falls down? They're like the size of a dinner plate.
I hate that so much. If someone ever did that to me, I'd probably have a heart attack and like pass out.
Fair enough. All right, capillary action. This is when water goes up a narrow tube. We have two forces at play here, cohesive and adhesive. So when water is moving up a tube, cohesive forces exist between the water molecules. Adhesive forces exist between the water molecules and the container. And so when you put water into glass, it starts creeping up the edges because water likes glass. Water likes touching glass more than it likes touching other water. And so it will maximize its glass coverage as much as possible. So when you read a meniscus, you have to read it from the very bottom because the edges are going to give you the wrong answer because it's creeping up due to some capillary action. The thinner your glass tube is, the higher the column of water would go. If you get to third year chemistry and physical chemistry 1, they'll run you through the mathematics of how high a liquid will go up based on the material and how thin it is. This is how water moves up trees in the xylem. It's just an extremely thin tube, and so water is evaporating from plant leaves through transpiration, and waters, as they evaporate, they're pulling on the waters below them. And you basically just have a train of water coming up. All right. If a substance makes no favorable bonds with this container, it'll form the opposite meniscus because it wants to minimize touching the container instead of maximize. So if the adhesive forces are greater than the cohesive forces, we get a convex meniscus. If it's concave, it's opposite. If the cohesive forces are greater, the liquid likes touching the liquid, it doesn't like touching the container. It tries to minimize it. If it's concave, that means the adhesive forces are greater. The liquid prefers touching the container as opposed to itself, and it creeps up the edges, giving you your concave meniscus. You almost never see the convex meniscus because in this class, water is always our solvent. Our graduated cylinders are made out of glass, and they'll curve up. And once you get to organic chemistry, you don't really pour things in the graduated cylinders. Everything's measured with syringes, and so you don't see it anyways. But in this class, you always read the meniscus at the bottom. They give you the most accurate reading. All right, boiling point. This is the temperature at which the vapor pressure of a liquid becomes equal to the external pressure. So once the vapor pressure becomes equal to external pressure, a liquid will boil, which means liquids boil at different temperatures depending what the pressure is on them. This is how a pressure cooker works. It applies pressure to the food you're cooking, and now that you're applying pressure, you can heat the water up higher than 100 degrees. It won't boil at 100 degrees because you've added more pressure. It might have to heat up to 130 before it boils Celsius, which means you can cook food a lot faster because it's a lot hotter. And just so that you have an apples to apples place to compare, we have normal boiling point. That is the temperature when the vapor pressure is equal to 1 atmosphere. Because boiling point changed with external pressure, normal boiling point just says external pressure is 1 atmosphere, and so then you can compare multiple different chemicals together. Otherwise, it would be unfair to compare diethyl ether at a pressure of 1200 torr to water at a pressure of 100 torr. And so having a normal boiling point has an easy apples to apples comparison for other molecules. And so the boiling point of water is 100 degrees Celsius. For ether, it's 35. Ether is a very volatile liquid. And for ethyl ether is 78. Petroleum ethers are called petroleum ether because they have about the same volatility as ethyl ether, and they evaporate about the same, and so they kind of mimic ethyl ether. But petroleum ethers are not ethers, they're pentanes, and so it's just a hydrocarbon.
So is that the same stuff that they use for like diesel engines and stuff like that?
You can. Ethers, yeah. Starting fluids use it. Methyl ethyl ether is used quite a bit. The vapor pressure curve for water is given below. What is the boiling point of water at 300 millimeters mercury? Well, we find our pressure, and we see it's about 76 degrees. Especially in organic chemistry, a lot of chemicals actually decompose and are destroyed at their boiling temperature. And so one way to distill them is to hook up a vacuum pump to your distillation apparatus and drop the pressure, because then something will boil at a much lower temperature. So water at 1 atmosphere boils at 100. But if we bring down the pressure to 100 millimeters mercury, now that water will boil at 50 degrees. And so you can distill a lot of compounds at a much lower temperature with this method, and so that they don't get destroyed. And so that's used a lot. Vacuum distillations used a lot with organic chemicals that way. Freezing and melting. A solid becoming liquid is melting. A liquid becoming solid is freezing. So we've covered 6 different things. A solid can melt to a liquid can evaporate to a gas can condense to a liquid can freeze to a solid can sublime directly to a gas can deposit directly back to a solid. 6 different phase changes that we have covered. When you're at a freezing melting point or an evaporation condensing point, the temperature stays the same. Like when you're melting ice, all the energy coming in goes into melting of the ice. And so the temperature stays consistent at 0 degrees the entire time you're melting. And once all the ice has melted into water, now the temperature will go up and you can get up to 100 degrees. And now it starts boiling. And as it's boiling, all the energy that you're putting into the water is going into the evaporation process. And so again, the temperature stays at 100 degrees Celsius until all the water has evaporated. And now that it's steam, now the temperature can go up again. So the temperature remains the same when you're at a phase transition. If you're switching from solid to liquid, or liquid to gas, or gas to liquid, or liquid back to solid, it stays at the same temperature until the process is done. The heat of fusion is how much energy is required to take 1 gram of a solid at its melting point and turn it into its liquid, still at the same temperature. So the heat of fusion of water is how much energy does it take to take 1 gram of ice at 0 degrees Celsius and convert it into 1 gram of liquid water, still at 0 degrees Celsius, no temperature change. All of the energy is going into the phase transition of solid to liquid. Heat of vaporization, how much energy does it take to take 1 gram of liquid water at 100 degrees Celsius, its boiling point, and convert it into 1 gram of gaseous steam, still at the same temperature of 100 degrees Celsius, its boiling point. And that is the heat of vaporization. For water, the heat of fusion is 335 joules per gram. It takes 335 joules of energy to convert a gram of ice at 0 degrees Celsius into a gram of liquid water at 0 degrees Celsius. So if I have 25 grams of water, the energy needed to melt it is 25 times 335 joules per gram, gives us 8,380 joules. Heat of vaporization. This is the, we just covered that. It's the energy it takes to take 1 gram of a liquid at its boiling point and convert it into the gas, still at its boiling point. For water, it's 2,259 joules per gram. Notice it's way bigger than heat of fusion. The heat of fusion for water was 335 joules per gram. Heat of vaporization is 2,259 joules per gram. It's 7 times more energy. Why does it take so much more energy to boil something than to melt something? It just goes to how many intermolecular bonds are you breaking. When you go from solid to liquid, you break a few of the intermolecular bonds, but most of them are still there. To go from liquid to gas, you have to break all of the intermolecular bonds, because in a gas, every particle acts independently and has no real attractive forces to one another. So to go from a liquid to a gas, you have to break apart 100% of all the remaining forces, which is a lot. And so heat of fusions are always way bigger than heat of vaporizations are always way bigger than heat of fusions. So to vaporize 25 grams of water takes 56,500 joules. Whereas to melt that, it only took 8,000 joules. So it takes a lot more energy to boil than to melt. Calculate the energy needed to convert 25 grams of ice at 0 degrees to steam at 100 degrees. There's 3 steps here. We start with ice at 0 degrees. We have to melt it to water at 0 degrees. And then we'll go back to chapter 4 with Q equals mc delta T. And see how much energy it takes to take water from 0 degrees to 100 degrees. And then we're at water at 100 degrees. We need to convert it to steam. We'll use the heat of fusion to boil that into steam at 100 degrees. So step 1, melt the ice. That took 8,375 joules. Step 2, the water rises from 0 degrees to 100 degrees. Which is Q equals mc delta T. The energy is the mass of the water times the specific heat of the water, which we remember from chapter 4, times the temperature change. 100 minus 0 is 100. And that's 10,460 joules. The last step is boiling the water. And we take our 25 grams of water times the heat of vaporization, and that is 56,475 joules. Notice that in this whole process, boiling took up like 2/3 of the energy. And that is one of the many reasons why steam is so dangerous. Because if it takes that much energy to evaporate water into steam, when steam condenses on something, it releases that energy. So if somebody is exposed to steam, a ton of energy is released on them and you'll have terrible burns. And then once that's done, now you have boiling water on you. So steam injuries always have the potential to be extremely serious, because of how much energy they release onto anything that steam condenses on. So working with steam is industrially dangerous.